This video, we're going to start chapter 3. So chapter 3 is just more techniques that we're going to learn that's going to help us differentiate technically any integral that we have. So in section 3.1, we're going to cover a method called integration by parts. So in this section, we're going to recognize what integration by parts means. We're going to use it to solve some integration problems, and then we're going to use it when we have definite integrals. Okay, so what's the difference between any method and integration by parts? So integration by parts is usually a technique we use when we have like a product rule for differentiation. So if you have a part of the product rule inside of your integral, integration by parts is a method that's going to help us differentiate what we have. So let's see how we derive the formula for integration by parts. Let's assume that I have a function h, which is a product of two functions, f and g. If we apply the product rule, we're going to get this. Now let's try and integrate along this whole equation. Integrating h prime, we're just going to get h using the fundamental theorem of calculus. And then here I can just distribute, and we're going to get these two integrals. So now if we take this part to the other side, not this one, sorry. If we take this to the other side, I'm going to get this. And now just renaming stuff. If I take u to be my f, v to be my g, then the derivative du is just f prime dx. The derivative dv is just g prime dx. Putting everything back into this formula, I'm going to get that the integral of u dv is just equal to uv minus integral v du, and that's our integration by parts formula. Now, I know it seems a bit confusing, but let's try one example to understand how this method is useful. So let's see here. If I want to evaluate x cosine of x dx, now if I only have an x by itself, differentiating it is easy. If I only have cosine by itself, differentiating it easy. But here, we can't distribute the integral. So this means I need to find another method to integrate x times cosine of x as a whole block. So let's try and take u to be my cosine. So if you take u as a function, you need to differentiate to get du. So the derivative of cosine is just negative sine of x dx. And then for dv, you take the rest of the integrand with your dx. So here we have x dx, and we integrate. So the integral of x is just x squared over 2. Then we are going to apply the formula. So it's just u times v minus v times du. So this is going to be x squared over 2 cosine of x minus always the integral of v times du. So negative x squared over 2 sine x dx. Now the problem with this choice of u and dv is even if we apply the integral, the integration by parts formula, we got an integral that's even more complicated. So when this happens, you know that your choice of u and dv might be wrong. So let's try a different choice. Let's take u to be your x. The derivative is just dx. You take your dv, the rest of the integrand, so it's going to be cosine of x dx. And now if you integrate cosine, this is just sine of x. And let's try and apply the formula. U times v minus v times du, so that's x sine of x minus the integral sine of x dx. So now if you see, we got an integral that we can use the antiderivative rules to find it directly. So here, integration by parts formula actually helped in finding the final answer. So here this is just x sine x plus cosine of x plus c, and that's your answer. Okay, so it's just applying the formula. The only thing that's difficult here is how do we choose which function to take as your u and which function to take your dv. So here you have to think about it smartly. I want to choose something as my u where I can differentiate and end it somehow. And I want to take my dv of something that I can integrate and integrate it easily. We also have this acronym that could help us. So we take this acronym, and this acronym stands for logarithmic, inverse, trigonometric, then algebraic, then trigonometric by itself, exponential function. So here, the type of function in the integral that appears first in the list, we take it as your u. So for example, if I got an algebraic function and a trigonometric function, since the a comes before the t, then I take my algebraic function to be my u. So let's see. For example, like the x cosine thing that we did earlier, if we want to apply this acronym to it, we got an algebraic function to be x, and then a trigonometric function to be your cosine. And since a comes before t, you take u to be your x. And if you go back, this is what actually worked. Let's try another example. If I want to evaluate ln of x over x squared. Okay, so x squared, I can write it as x to the negative x, to the negative 2, sorry. Now, which one should I choose as my u? Should I take x negative 2 as my u or my ln of x as my u? If you go back, you see that logs always comes first. So since I have a log function, which is ln of x, I always take it as my u. So now, if you differentiate, this is just 1 over x dx. And then your dv, you take it to be the rest of your integrand. Now we're integrating this, so the integral is just x negative 3 over negative 3. So now this is equal also to x negative 1 dx. Now applying the formula again, u times v minus the integral of v du, we're going to get negative ln of x over 3x cubed minus the integral of x negative 3 over negative 3 multiplied by x negative 1 dx. And now this part here, we can easily integrate. Okay, I think I made a mistake here. This should be x minus 1 because we add 1. Sorry for that. So this is x negative 1 over negative 1 multiplied by x negative 1. If you simplify, I need to fix it here too. This is just x without the 3. So negative ln of x over x plus, so this is x to the negative 2. If you integrate it, you're going to get x to the negative 1 again, plus c. Okay, so how about if I have x squared times e to the x? Now, this is an algebraic function. This is an exponential. And if you go back to the acronym, algebraic comes before exponential, so I need to take x squared to be my u. So if we take x squared to be your u, your du is 2x dx, your dv e to the x dx. The integral of e to the x is just e to the x. And applying the formula, u times v minus v times du with the integral. Now if you look back here, technically we did not solve the problem because I still have two functions that I don't know the antiderivative for directly, so I might need to use integration by parts again. So here, if you apply integration by parts again, you'll take your u to be 2x, your du is 2 dx, dv, in the same process. You apply it again, uv minus integral v du. Okay, so here be careful. If you started with a certain integration by parts by taking your u to be a certain function, if you want to apply it again, you need to take the same function again. So here I can't take e to the x here. I need to take 2x, the thing that I got from my du. And like if you think about it, this is correct applying the same acronym because algebraic comes before exponential. So now applying that again, we're going to get 2x e to the x minus the integral of 2 e to the x. Now, how do we know when to stop? We stop when we get an integral that we can find using the antiderivative rules directly. So here I know how to integrate e to the x, so I'm done. If we distribute the negative plus c. Okay, you might be wondering why when I integrate from dv to v, I'm not putting plus c here, even though it's an indefinite interval. So the reason why I don't write plus c is because even if I write it, obviously like the correct thing is always to write plus c when you're doing indefinite integrals. But here, since if I write it as plus c, I'm going to have it in one of these terms, and then I'm going to have a plus c here in one of these terms, and I have a negative, so this c is going to kind of vanish because I have c minus c is going to be 0, so that's why we don't even bother of writing it when we integrate our dv. Okay, so let's see here. So usually when you have a function and you want to apply the acronym, for example, if I have this example here, you're just going to take your u to be t cubed, your du 3t squared dt, but if you try to integrate e to the t squared, because you have to take it as your dv, you're not going to be able to integrate it because you don't know how to integrate this. No u substitution or any antiderivatives would give you the answer. So here we want to apply the acronym, but we need to be a bit careful. So here, instead of taking your u to be t cubed, you can try and take it to be t squared. Let's try if that helps. Now your du is just 2t dt, your dv is t times e to the t squared dt. Now let's try and find v. V is just the integral of dv. Now if you look closely, a u substitution here is going to be helpful. Let's call the u substitution u1, just to differentiate it between this u and this u. So here, if you take u1 to be t squared, if you take the derivative, this is just 2t dt. Then your du1 over 2 is just d dt, which is what we have here. Then, if you apply the substitution, you're going to get e to the u times du1 over 2, and you can integrate it easily. This is just eu1 over 2 plus c, but we said we don't have to write plus c here. So this is just e t squared over 2. So now, if you put it back using the formula, u times v minus the integral of v du, we're going to get t squared e to the t squared over 2 minus the integral 2t e to the t squared dt. But if you look closely, this integral that we got here requires a integration by parts again, because we did not get to a point where we know the value of the integral directly. But this integral technically is the same as this one. So instead of doing a u substitution again, I'll just take the same answer. I have 2 on this side, and then the integral of t, e to the t squared is just equal to this. Then plus c in the end. And we're done. Okay, so always when doing integration by parts, think about u is something I can differentiate, dv is something I can integrate, and see if you need to apply the integration by parts method again. Okay, so let's look at example number 4 here. What if I want to integrate ln of x dx? Now, if you look at the functions, I only have a log function here. I only have ln. Well, if we're applying the acronym, I know that my u is always going to be a log function if I have it in my integral. So I'll take u to be my ln of x. du is just 1 over x dx. But what should I take as my dv? So if you look at the integrand, I don't have any other functions. So when no obvious function is there, your function is technically just a constant function 1. So here I just have 1 dx. If you integrate it, this is just x. Now applying the rule again, you're going to get ln of x minus the integral of v du. These cancel out, so I just have the integral of 1. So this is just x ln of x minus x plus c. Now integration by parts with definite integrals is technically the same. The only thing different here is I need to apply the bounds to my integral. So instead of just multiplying u times v, I need to substitute the bounds a, b, upper minus lower, and we integrate here with the bounds too. So for example, if I have this integral, I have algebraic exponential, so obviously my u is going to be just x. Oops. My du is just dx, then dv you take the rest. And now to integrate here, you might need to use a u substitution, but I can integrate it easily and get this answer. Then applying the rule u times v minus the integral that we have. But since I have a definite integral from 0 to 1, I need to plug in 0 to 1, 0 to 1. So here, if you plug in 1, you're going to get minus 0. Then we can integrate this from 0 to 1, upper minus lower. You'll get this answer. And since we're doing a definite integral, we don't have a plus c. Okay, so that's it for integration by parts. Just be careful with choosing your u, and once you know your u, you'll be done basically. You just apply the formula. Sometimes you might need to do a try and error where you take a u to be a certain function. If it doesn't work, if you get the new integral is more complicated, you know that your choice is wrong and you need to go back again and do a different substitution for your u and apply the formula again, and you'll see if that works or not. So see, these are some suggested problems from section 3.1. Try and do them if you need extra practice. Okay, so the second section that we're going to cover today is section 3.2, which is trigonometric integrals. So nothing new here. It's just some properties for sine and cosine, tan and secant, where if you have a multiplication of these two functions and you want to integrate them, you want to have a way to integrate them easily, because we don't know the antiderivative for a product of these functions directly. So what we're going to use here is we're going to use some u substitutions for some questions And we're also going to use integration by parts actually to solve other problems. And in the end, we're going to talk about reduction formulas that might be helpful to integrate things quickly. So let's start with the first case where I have a product of sine and cosine. So the first case is when I have cosine to a certain power multiplied by sine by itself, or if I have sine to a certain power multiplied by cosine by itself. So here we use u substitution directly. So you take your u to be the thing that has a power. Because here, if you look at it, the derivative of cosine is already there. It's negative sine. I'll just add a negative. And the derivative of sine is just cosine, and it's already there. So I can use u substitution directly. So for example, if I have cosine to the fifth multiplied by sine, I use u substitution directly. I'll just take u substitution to be cosine, find the derivative, and then plug everything back. So I'll have the integral of u to the fifth multiplied by negative du. If you integrate, you're going to get u to the 6 over 6 minus plus c, and just plug the substitution back in. So it's pretty simple here. Now, what if we have two powers for sine and cosine? How do I know which method to use or what substitution to use? So here we have some cases. In the first case, if my k is odd, which is the power of my sine, we do a u substitution, but we take u to be cosine. And then we're going to use this identity that's going to help simplify our question. And similarly, if I have j to be odd, I'm going to use a u substitution, but my u would be a sine, and I'm using the identity of this form. So let's look at this example. I have cosine squared multiplied by sine cubed. Now, since sine is the one with an odd power, you take your u to be cosine. You differentiate and see what happens. So now I can write the integral cosine squared multiplied by sine squared sine dx. So the reason why I wrote it this way is because du is sine dx, and I want to get sine dx somehow. And then since I have a substitution in terms of cosine, I want everything in my integral to be in terms of cosine. So I can write the sine squared as 1 minus cosine squared using the identity, then leave sine dx by itself because I'm going to need it to substitute du. So now if we plug in the substitution, this is just u squared, 1 minus u squared multiplied by negative du. You distribute and integrate, and you're going to get this, and plug in your u back in. With practice, you're going to notice a pattern of the way what u substitution you want to use, or whether you want to use integration by parts. So here, if both k and j are even, we're going to use these two identities and then apply the strategy that we did here again. So let's see, if I have cosine squared of 3x, so here j is 2, k is 0, so both are even. So if both are even, I'm going to use strategy number 2 and use one of these identities. Now cosine squared is 1/2 plus 1/2 cosine of 2x, right? But my x here is 3x, so I'm going to plug in 3x. So this is 1/2 plus 1/2 cosine of 6x. And don't worry about memorizing all of these identities. I'm going to provide them all in the exam. So, because math is not about memorizing, it's about knowing stuff and knowing how to apply them. So just focus on understanding the methods and how to actually evaluate the integrals and all of the identities will be provided in the exam. Okay, so now back to the question. I know that cosine squared is equal to this, so I'm just going to plug it back in. And now if you see, I can integrate this directly. This is just x over 2 plus cosine 6x over 12 plus c. I went from cosine, oh sorry, this is sine. I went from this to this using a u substitution of 6x. Now how about if I have cosine squared, sine squared, both even, then strategy number 2. So here I need to apply the identity twice. One's for cosine and one for sine here. And now this is a difference between two squares, so this is just the integral of 1/4 minus 1/4 cosine squared 2x dx. So this part is done. Now for this part, technically I need to apply the same strategy number 2, because I have cosine squared. But you can do the same thing as we did here and get the answer that you want. Now we have these useful identities that could help us integrate when we have different angles of sine and cosine. Again, these identities would be provided in the exam if needed. So let's use one of them. If I have cosine 6x, cosine 5x, how would I integrate? Because here I can't combine them into cosine squared because we have different angles. So to use it, I'm just going to apply this identity here. So this is just 1/2 cosine the difference of the angles. So it's 6 minus 5, so it's just x, plus 1/2 cosine the addition of the angles, 11x dx. And again, we can integrate easily. I apply the substitution here. Okay, so this is for sine and cosine. Not too bad, right? How about if I have tan and secant? We're going to apply similar methods. Let's just recall the integrals of these. So these integrals we should know. And now let's see. If I have a secant with a certain power and tan by itself, I'm just going to use a u sub with u to be my secant. If I have tan with a certain power and secant squared, I'm going to apply a u substitution directly with u to be tan. That's it. But we always have to have secant squared. So the reason why I need to have a secant squared, because the derivative of tan is secant squared, so that's why I need to have it here. Because once you differentiate du, you're going to have secant squared dx, so I need to have it here. So let's try this example. I have secant to the 4th, tan of x. Secant to a certain power, tan by itself. I'll take a u sub with secant. Now the derivative of secant is secant tan. And let's plug everything back in. I'll take one of these secants with the tan, and that would be my du. So I'm going to have secant cubed secant tan dx. And using the u sub, this is just u cubed times du. Integrate and plug back in, and you're done. Now what happens if I have powers for both tan and secant? So here we also have different cases. If the power of secant is even and it's bigger than 2, we use a u substitution with u equals tan, and we're going to use this identity. So let's try it. If I have tan to the 8th, secant to the 4th, so here tan is with even power. So I'm just going to use a u sub with u to be my tan. If you take the derivative, this is secant squared dx. So if you take secant to the fourth as secant squared dx, and then one of these secants I'm going to use this identity for, because I need something to be all in terms of tan, because that's my u. If I have things in terms of tan and secant, I won't be able to use my u sub directly. So here I have tan to the 8th tan squared x plus 1 multiplied by this. And we leave this because we're going to use it with the du. So now using the u sub, we're going to get this, and you can do the same exact process. So I know it's like a lot of strategies that you need to know, but with practice, you're going to notice how to use them directly. You don't even have to memorize which u sub you're going to use, whether like j is even, k is odd, or whatever. You just need to practice and notice that, oh, since I'm doing u to be 10, I need secant squared somewhere. But if I have secant squared, oh, I need to substitute it with something in terms of 10. Oh, and I know this identity, so I'll just apply it and integrate easily. Okay, now what if we have k to be odd and j anything bigger than 1? Here, we're going to use a u sub with secant and this identity. If j is even and k is odd, we can either use 1 or 2. It doesn't matter. You can try it with this example, and you'll see that both work. So here, let's take our u to be secant, because k is odd and j is bigger than 1. This is secant tan dx. Now I'll take 1 tan and 1 secant, and then we're going to have a tan squared x right here. I'll just write it this way so I can easily find it. But tan squared is just secant squared minus 1, which is perfect because I need everything in terms of secant. And now secant tan dx is just du. So this is the integral of u squared minus 1 multiplied by u du, and you can distribute and find the answer directly. Now if we have k to be odd by itself, so I only have a tan in my question. Tan with a negative exponent, with an odd exponent, sorry. So to do that, we're gonna take a tan squared by itself and see what happens. So here, if I have 10 to the 5th, I want to separate my tan to the 5th to be 10 cubed times 10 squared. Now 10 squared, I know this is equal to secant squared x minus 1 dx. If you distribute, you're going to get tan cubed secant squared minus the integral of tan cubed dx. Now, tan cubed is again a k with an odd power and j equals 0. So I'm going to repeat the same process again. So that's why we need to repeat it if needed. And now this part here is just the same integral that we did here with tan odd secant even. This one. It's the same process. So now I'll give you the answer in the end. This is just secant to the 4th over 4 minus secant squared x for this part, using the example that we did above. Now here I need to apply this process again. We separate the tan by taking tan squared by itself. Then tan squared is just the secant squared minus 1 dx. You distribute Let's see what happens. Oh, there's a 2 here. Now, once you distribute, you're going to get tan secant squared plus the integral of tan. Now, the integral of tan, it's given in the table of antiderivative. It's just ln of secant. Now, tan secant squared, if you remember, the derivative of tan is just secant squared. So I can just do a u sub with tan. And my du is just secant squared dx. So technically, this is just an integral of u. Let's write it on the side so you can see. So this is the integral of u multiplied, we have a dx here, secant squared dx is just du, so this is u squared over 2. But my u is tan squared over 2, so I have a minus tan squared over 2 plus ln of secant x plus c. And the last case that we have is k is even and j is odd. We're going to use this identity to express tan of the even power in terms of secant, and then we're going to use integration by parts to integrate the odd powers of secant. So let's try here. I have the integral of secant cubed. So secant cubed is an odd power for secant and 0 for the tan, which is even, so I'm going to apply this. So here, since I don't have any tans, I'm not going to do anything. The only thing I'm going to do, I'm going to jump to step number 2 and just use integration by parts. So by using integration by parts, you're going to take your u to be just secant. Your du is just secant x tan dx. dv is secant squared. So the reason why I chose secant squared here, because I can integrate it. So if I integrate secant squared, this is just tan. Now applying the integration by parts formula, u times v minus the integral of v times du. So this is secant tan squared x dx. So now what do we do? Let's look. I have k to be an even, j to be odd, so I'm going to apply strategy number 4 again. So what we do is we write the tan in terms of secant using the identity. Let's try and distribute and see what we get. So we have secant cubed plus the integral of secant x dx. Now the integral of secant is easily evaluated because I know the formula. It's just ln secant plus tan. But how about secant cubed? The problem is, I started with secant cubed, and after doing integration by parts, I got another integral of secant cubed. So technically I did not solve any of the problems that we have. But if you think smartly, I can take this to the other side and just add them together and get one unknown integral. So now if you take it to the other side, you're going to get 2 secant cubed dx, which is perfect because this is what we want. And it's going to be equal to something that's already evaluated, secant x tan of x, then plus the integral of secant, but we know this is just ln secant tan of x plus c. So technically we're almost done. I just have an extra 2 here, so I need to divide it all the way. So now the integral of secant cubed dx is just 1/2 secant tan plus 1/2 ln secant plus tan plus c. So I know it's a lot of cases, it's a lot of methods. So just keep practicing until you get an understanding of what exactly am I doing here. Do I need to use a u sub? Do I need to use some identities? Obviously, if it's better for you to memorize. You can memorize some of the strategies and just keep applying them. But the best thing here is just keep practicing, so you'll get, like, you'll create your own pattern of like how you're gonna do a use up, or like identities, or even integration by parts. And the last thing that we're gonna talk about today is some reduction formulas to evaluate secant to a certain power and tan by a certain power by itself. We have these two formulas. Again, these formulas would be provided in the exam if needed. So let's try and evaluate secant to the fifth. If I try to apply this method, strategy 4, obviously it's going to work, but it's going to be a very long process. But we're going to get the same exact answer in the end. So here, instead of doing strategy number 4 and doing a lot of steps, I can just apply the reduction formula that we have here with n equals 5. So this is 1 over 4 secant 5 minus 2, so that's 3, tan plus 3 over 4, the integral of secant cubed dx. Now, we evaluated this using strategy 4, and it took a long time, right? But now if I apply the formula again, because I don't know how to integrate or like find the answer of integral of secant cubed directly, but it's of this form, so I can apply the reduction formula. So this is 1 over 2 secant tan plus 1 over 2 the integral of secant x dx. If you look back, it's the same exact answer, which means that this formula works and gives us the same thing. Oops. Yeah. Now you can integrate this easily using the antiderivatives and simplify. So these are some suggested problems if you want to do them and get extra practice. And if you go to Lumen Homework 3, you can do these problems. Make sure to practice, and if you have any questions, if you want me to repeat any of these strategies, just let me know, email me, and I'll be happy to help you. Enjoy the rest of the day and good luck.